Okay, good afternoon. Welcome back. It is Thursday today, the 26th of March, and hopefully you've gotten some emails from some of your coordinators about what the schedule looks like, and you're able to either join or rewatch videos that are applicable to you. My intent is to keep labeling them the way that I am, which is with the course title and then like a topic title. So, for example, a couple days ago, Algebra 1 and 2. So if you're in either of those classes or in any of the intermediate math classes, integrated math classes, depending on what your school offers, hopefully a lesson on the equal sign is useful. Yesterday's was a geometry session where I looked at parallel lines cut by a transversal. So if you're in a geometry section, and again, that can be the integrated math courses as well. So you may not know this, but different schools do different setups. So some of you actually have a geometry class, say as sophomores, and some of you are in integrated courses where you might do geometry every year of 9th, 10th, and 11th grade as part of the course. So if that is applicable to you, go ahead and look at it, and I'll keep trying to title it appropriately. So today's lesson will be the beginning of a longer sequence on polynomials. So it's going to be a topic that I come back to and back to and back to because it's just, I don't know, it's the heart of it, right? It's really the heart of algebra in a lot of ways to understand these types of things. So I could have started with variables, but we're mid-semester, right? If I was starting this up in September or in January, I would do things different. But let's talk about polynomials. So the first thing about polynomials that we want to know about is, well, actually, let's just look at some examples. So polynomial, the typical one, x, right? Very common. You probably have also seen x squared. You've seen x cubed, so on. But also our numbers, right? So any number here is also a polynomial. We'll talk about why. But the key here is that it's some relationship between an input x and a power, a whole number power. So for example, a relationship p of x that doubles x and then subtracts 1 from that total. We know that it's a line, right? We're familiar with lines with slope 2, y-intercept -1. So there's a lot about it that we can know about. Kind of, let me sketch very roughly what that might look like. Something like that. But why is it a polynomial? Well, it's the sum of powers of x, right? Whole number powers of x. Here, and this is important, is an implied 1, right? So I can actually go up here and write that as well. There's an implied 1 here. Here is actually an implied x to the 0, okay? Now we know anything to the power 0, so anything to the 0 power is 1, right? So that often we don't write ones, right? That's a 1, and it's implied. We deal with all these numbers, right? 2.731 x to the 0, but we never really write x to the 0, or not that frequently. At times, maybe, but in most cases, no. Because it's inconsequential, right? It doesn't matter what x is because it's being raised to the 0 power, it's always 1. So it doesn't matter that x can vary. it's not going to influence the overall value of 2.731 times x to the 0. Now that's very different than saying 2.731x to the first, right? That there x does matter. If x is 1, if x is 2, if x is 7.6, matters, right? So we have polynomials, and they're a major part of what we're doing here. Couple of concepts to think about. The first is degree. Okay, degree is the highest exponent or power in the polynomial. So let me do a couple examples here. Let's do 3x minus 1. Let's look also at 4x squared plus 3x plus 15.7. Let's look also at x minus x cubed. Let's look also at 5. So each of these 4 as a polynomial, right? 1, 2, 3, 4 different polynomials. What is their degree? It's the highest exponent of x, so I should maybe add that here, of x, in the polynomial. So here, let's look through it. Well, let's look at this polynomial, number 1, 3x minus 1. It's a line. Slope 3, okay, y-intercept -1, all right. What are the powers of x? Well, this has an implied power of 1, and this has an implied power of 0, so 1 is its degree. Number 2, implied power 1, implied power 0 here, so we got 2, 1, and 0, so degree 2. For number 3, x minus x cubed, implied power 1, power of 3, there's the degree. And finally 5, it's x to the 0, 0 is the degree. Okay, so that's a concept that'll keep coming back, and I'll kind of talk that way in terms of saying like, okay, what's the degree of this polynomial as we look at things? But I want to reset here for a second and take it to another difficult concept here. Which is one that I've spent a lot of time with in some of my courses in the past. And that is the concept of end behavior. So I want us to spend a little bit of time looking at how polynomials look, right? How they look. So let's start with an example here, p of x to be x plus 3. Okay, so take our time, a deep breath. We're looking at the polynomial x plus 3. Now, based on what we just talked about, the degree of p, or of p of x, is, hopefully you see it, degree 1, right? It is a degree 1 polynomial. It's a line. X to the first, I'll do this in red, because it won't frequently be written. Remember, this red writing is often implied. X with no power written doesn't mean it doesn't have a power. It means that that power is 1. Plus 3 with no x written doesn't mean x, it just means x, the x to the 0 power doesn't have any influence, so no reason to write it. X to 0, always 1, 3 times 1, always 3. So we just write 3. Makes some sense. Now, what is end behavior? Well, we're getting there, but let's think about first a graphical look at this line. Okay, off to the side here, let's recall lines take the form mx plus b That's slope-intercept form, or can take the form. You can manipulate lines that aren't already in that form to look that way. Mx plus b, the slope m here is 1. That 1, another implied 1. 1 times x to the first. Neither of those 1s are written because they're not influential. 1 times x, always x. X to the first, just x. There we go. So 1x to the first, just written as x, but it's meaningful because having a slope of 1 is meaningful. It shows us something. Having a y-intercept of 3, positive 3, note for a second that how this looks like mx plus b. The pairings here, b and 3, x and x, m and 1. So, all right. Okay. All right, so it's a sketch, but it's a little more precise than some of my sketches, in that I actually tried to hash out correct points and put them down and connect them. But I don't have a ruler. Well, I don't know how this thing works, but I can look at it maybe later. Okay, so there it is. But it's a casual thing, but it's incredibly influential. It's actually these two arrows that I've drawn, right? This arrow and this arrow. Those are incredibly important symbols in our graphing mathematically. They indicate this will continue on this trajectory forever, indefinitely. So we are indefinitely going up and to the right. We're indefinitely going down and to the left. Because it's a line, it's an incredibly consistent rate of going that direction, right? It's not like it's not speeding up like that. It's not slowing down like that. It's just going off forever like that. And similarly down this way forever. But we don't draw it, obviously. Spatially, it would be redundant, right? We're going to have to visualize it as opposed to using the space and paper or this visual space to actually draw it on. I mean, you could imagine like why we wouldn't do it if eventually I run out of space. Well, should I scroll up and keep going? I could. That's what's happening. I could. But I generally don't, and you generally won't see it this way. And when you graph and you want to indicate, okay, this is going to continue in this type of trajectory forever, we use arrows. Now, those arrows are indicators of this initial idea here, end behavior. So the end behavior is a concept that asks, what happens vertically to the graph as we move extremely out to the right and extremely out to the left, right? As we keep going, what happens vertically? Well, you can kind of see, right? Like as I keep going right this way, what happens to the blue? Well, it keeps going up, right? I keep going right, it would keep going up. All right, and up, so on and so on and so on. So an end behavior, meaning to the sides, end behavior, it's a decent term for what we're talking about. I'm not sure what would be better, but it's essentially like what is happening in the very, very extremes as we go out forever. So it's a very, you want to visualize it or sort of play it out in your mind that like if you wanted to keep going to the right, you would keep going up, right? Keep going up at the same rate. If you want it right over and over and over and over. And you can imagine what the implications of that are, that you want to go out and out and out to the right, going up and up and up. So that is an end behavior. As we go right, we go up. Similarly, the same line, we're still talking about x plus 3. What happens as we go left? Well, as we go left, we go down. As we go left, we go down, right? Now, they seem to be happening simultaneously, but this is somewhat of a relationship between the dependent and independent variable, right? X we get to pick to some extent, right? We're just thinking like, let X be very, very small or very, very large negative numbers, right? What will happen to Y? Well, it will keep going down. You can see, right? In this line that we're talking about, x plus 3, let x be negative 10. Well, y is negative 7. Let x be negative 100. Well, y is negative 97. Let x be negative 1,000. Well, y is negative 997. So on, so on, so on. Go left, go left, go left. Go down, go down, go down. All right. So that is also end behavior. Go left, go down. Go far left, go far down. Okay. So that's a language base of it. But let's actually write out some of how this might look. So our polynomial, again, is we're looking right now at x plus 3. As x goes right, meaning goes very far to the right, goes to positive infinity over here. X, right? 1, 2, 3, 4, 5, 6, 7. X goes out, 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 out. What if it just keeps going out? What happens to y? Well, we know, right, up, right, go up for this line. So as x goes right to positive infinity, far out to the right, y goes up, far out to the right, far up, right? So it keeps going, 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 going. So as x goes to the right, y goes up. And the infinity is, yes, it's kind of directional, right, as x goes, but it's very specifically talking about very, very extreme to the right movement, very, very extreme to the up movement, as opposed to like looking in here and saying, let me make a conclusion about end behavior. We're very specifically thinking this is a line. It's the arrow that's telling us. I know obviously we would have to pick to draw the arrow or know to draw the arrow, but it is a line, so it continues off in the same direction at the same rate. So we have that. Similarly, think about this. As x goes to negative infinity, think about what that means. As x goes to negative infinity, this being y, this being the x-axis, what happens to y? First thing is to know this means what happens as we go very far to the left, very, very far to the left. X being to negative infinity, which is a direction, right? Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, so on, so on, so on, so on, so on. Way, 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 way out here, right? Off the charts. We're off the charts. Way out there. What happens? Well, we see it. We've drawn it. As we go left, we need to go down to look at our graph. So y also goes to negative infinity. Okay. So those are end behaviors. You might have already heard the word asymptote. Asymptote has a lot to do with what's happening here, or can, in certain circumstance. So end behavior, if you've done rational functions, right, which we'll look at sometime in the future. Okay. And let's just make one more note here. Remember that p of x equal to x plus 3 is a degree 1 polynomial. That will matter. That will help us in the future. We're going to establish patterns. We're going to establish an expectation. Oh, I forgot. I'll have to erase all this work where I was showing these end behaviors. So I won't be as extreme in demonstrating it in the future, so I don't have to do that. Oops. Oh, nice. Figured out how to zoom out. All right. Zoom back in a little bit. That's probably good. Okay. Now, another polynomial, one we're definitely familiar with. Let's do q of x equal to, how's negative x squared plus 4? Negative x squared plus 4. Likely, depending on what grade you're in, what courses you've taken, you have looked at this type of polynomial. You might not have referred to it as a polynomial. You may have referred to it as a quadratic or a parabola. Those words, quadratic, spelled it wrong there, a parabola, refer to degree 2 polynomials. So the polynomial is more general. It doesn't have to be degree 2. Just like a line refers to degree 1 polynomial. A polynomial doesn't have to be degree 1 or 2. It could be 0, 1, 2, 3, 4, 5, 6, so on, so on, so on. But these ones are a little bit more common, or even a little bit more simple to deal with because they're lower degree, their shape and things like this. So we generally start with them and give them special names. Of course, the line, of course, the quadratic. Now, even degree 3 has a name, cubic, and so on. There are some other names, but these are the most common. So you know about this one likely. But if you don't, let's do a little bit of discussion. Of course, it is a degree 2 polynomial, right? That's the highest power. Note that even if I had written it as this, which is equivalent, so negative x squared plus 4 or 4 minus x squared equivalent, it is still a degree 2 polynomial, despite the fact that this is 4x to the 0. So it doesn't matter where the highest power happens in the expression of the polynomial, just which one is it. So you have to look at every term, establish what its degree is, and then figure out, establish what its power is, and then figure out which one is the highest. So those are equivalent, right? Right, those are equivalent. They're the exact same quadratic, and they're all degree 2. Now, how does it look? Well, when x is 0, y is 4, right? Q of 0 is negative of 0 squared plus 4. That's 0 plus 4. That's 4. So that's on there. Then maybe we'll look left and right by 1 to the x value. So when x is negative 1, when x is positive 1, what happens? Well, it's negative 1 squared plus 4. Okay, that's negative 1 plus 4. That's 3. Now, you may already know this about quadratics. They are, in fact, symmetric to the left and right of their vertex, which we happened to find. It doesn't have to happen at 0 for every polynomial, but it does for this one, for every quadratic, excuse me. So, okay. Also 3. And you might see pretty quickly in this expression, if x is 2 or negative 2, y will be 0. So this is what this looks like. We can start thinking if x is 3, y will be negative 5. If x is negative 3, y will also be negative 5. If x is 4, y will be negative 12. If x is negative 4, y will also be negative 12. There's a nice symmetry here. And it is rocketing down, right, as we go right and left. It's going down fast, right? Let x be 10. 4 minus 10 squared, 4 minus 100, negative 96. Right? So it's really, really going down fast. faster than the previous line was going up or down. It's going faster. But it is still having somewhat of a similar description when it comes to end behavior. As we go very far to the right, we are going down, right? Going right, going down, going right, going down, going right, going down. Now we go a little bit to the right, we go a lot down, but we go a lot to the right, we go even more down, right? Similarly here, we go left, we go down, right? Left and down. And really even the part that I'm highlighting is in some ways a bit of a misdirect, because we're not super interested in like what is happening in a specific place. We're looking at the pattern, what will happen consistently once we get large enough to the right on x. Does y act in a patterned way or in a predictable way? Well, yes, it does in this case. If we go very far to the right, we go very far down. If we go very far to the left, we go very far down. Okay. So we always ask these two questions when we're thinking about end behavior. We are thinking about what happens as we go far to the right, what happens as we go far to the left. Well, take your time, look at it. What happens as we go far to the right? What happens to the outputs of Q as x gets very large, positive? What happens to the outputs of Q as x gets very large, negative? Well, they go very far down. Very far down. Okay. My intent next week is to pick this up, kind of right here. But let's actually look at just one more case, one more example to think about here. Yeah, we can do it in not a ton of space. So let's let f of x be 5. F of x is a number here, it's equal to 5. However, it is also a polynomial, 5x to the 0. It's also not a point, right? 5 being a single number doesn't mean it's just a single point. This is a line. F of x here is a line. What type of line is it? Well, you might know. It is a horizontal line. It's this horizontal line. Okay, I didn't do great at hitting where I had hash marked 5, but you get the point, right? 0.5 is on there, 3.755 is on there, negative 2.65 is on there. These are, any x input you want, y output 5. So sometimes we see it labeled like that. When I'm sketching, I don't always follow through with good practice here of labeling our axes, but there you go. X and Y axis, or input-output axis. Okay, it's a horizontal line. It's a horizontal line. What does that mean for end behavior? Well, first of all, it's a degree 0 polynomial, if you recall. The highest power of x is 0. 5x to the 0. So it's degree 0. But let's think about our end behavior statements. As x gets very large, very far to the right and left, what happens to y, the outputs? And these arrows kind of shorthand for goes to or approaches. Well, what happens to this horizontal line output as x gets very far to the left or to the right? Well, it not only goes to 5, it actually is 5. It's always 5. It's not changing. It's always 5. So this is an interesting case of an end behavior where we're not going very far up or down as we go very far left and right. We're actually staying very consistent right at 5 always. Okay, hopefully that was a helpful couple of examples for thinking about polynomials again. We're going to talk about like adding, subtracting, multiplying, dividing, factoring. We'll do more on this. We're going to establish what the pattern here is, like the more general patterns for end behaviors when it comes to polynomials. But the thing to take away about end behavior, what happens as the inputs get very, very large and very, very large negative, very far to the right, very far to the left? What happens to the outputs? Okay, thanks for joining or rewatching sometime in the future, and I'll see you next time.